Hi everyone, I'm Sheng Wang, a PhD student at the Australian National University, and I'm supervised by Harvey Keldridge. Today, I present the inner core shear wave entropy revealed by CODA correlation wave field with global networks. As researchers in earth science, many of you are like me, rely on observations from networks, for example, seismic networks. The seismic networks are undergoing dramatic expansion nowadays. For example, in the left is seismic networks in different colors that are recently accessible on ARIES. It is important here to highlight some continental scale networks, such as the US array in continental US, and importantly the AuScope networks in Australia continent. We are now having more and denser stations in Australia, as shown by these different color symbols, expanding with time. With global network observations, we can explore the Earth's interior. For example, here is an earthquake that can generate a seismic wave that penetrates the Earth's interior and get recorded by network stations called seismic waveforms. These seismic waveforms can be used to study the property of Earth's internal structure. For example, the anisotropy structure. The anisotropy describes the variation with direction, and it is highly related to many valuable underground information, such as the aligned crystals for specific minerals, and the aligned fractures and melting liquids, and even the sedimentation that are highly related in oil explorations. Here is an example, the entropy for two cakes. You can see the left one has a very clearly layered structure, while the right one inside is well mixed. Therefore, the left one is strongly isotropic, and the right one is weakly isotropic. That means we can use the anisotropy to distinguish between them, or even we can put some sensors on the cake to quantify the information within the cakes. That is similar to what we are doing for our Earth. In this talk, we will focus on the entropy in the Earth's inner core. The inner core is important for whole planet evolution and dynamics. For example, the inner core made of iron is cooling down inside the liquid outer core, and that process is responsible for the formation and the variations of the Earth's magnetic field. Also, this progress is like a power source that helps drive the mantle convection that is responsible for the plate movement. The inner core entropy. Many studies have found out that when a seismic wave penetrates the inner core, it will travel faster in directions nearly parallel to the Earth's rotation axis than other directions. But this is only observed for compressional waves or P waves, represented here. So any of us can ask, how about shear wave? Can we observe shear wave entropy inside the inner core? However, shear wave entropy in the Earth's inner core has been elusive in observations. To our best knowledge, there's only one study for direct observations until now. So you can imagine the difficulties behind. Motivated by that, in this study, we will show you a new class of observations for shear wave entropy in the inner core based on global networks. Now, data and method. We use CODA correlation wave field. So what is CODA correlation? Here are examples for seismic recordings. You can see clear and strong signals. And after these clear and strong signals, we can see relatively weaker recordings, the later CODA. CODA means tail, like the concluding passage of a music. So imagine when you are in a concert, the concluding message will be the most charming and fascinating part for the mixture of many instruments and emotions, like here, a mixture of complex signals. They are like noisy and seems useless. But we can use two techniques, interstation cross-correlation and stacking, to transform the complex and seemingly noisy and useless later CODA into a 2D image called a CODA correlation wave field. This correlation wave field has many prominent features, such as this one, the I2 minus J. Here is the seismic array for I2 minus J. You can see it samples the Earth's inner core as shear waves represented by this dashed line. Then we compute for global network observations. Here we compute different correlograms for different event receiver geometries. We get a different correlation wave field for I2 minus J. From analysis, you can see that there is a time difference between them, and it's about 5 seconds. It is related to the different sampling of the inner core by I2 minus J. So for producing these different correlograms, this is all the stations and events we used on global scale. I would like to say without global networks, it's impossible to observe such time difference for the inner core shear wave entropy. And then we do analysis to confirm that time difference. And we analyze several explanations for the time difference. And finally, we conclude that the inner core shear wave entropy is the simplest and the most plausible explanation for our observations. Then, from our new observations, we would like to learn about minerals inside the inner core that is responsible for the entropy. We all know that the inner core is made of iron, and the iron can have crystals in body central cubic structure (BCC) or hexagonal close-packed HCP structure. There are two candidate crystals inside the inner core. For them, we simulate the entropy and compare the simulation with our observations. As you can see here, one of the curves for the entropy is opposite to our observations. That is for BCC 001. That means we can exclude this model, this crystal, inside the inner core. To conclude, we provide a new class of observations for shear wave entropy inside the Earth's inner core with global network observations. We obtained the entropy properties for its strength and its alignment. And with this new observation, we can rule out one iron crystal structure inside the inner core, although we can't uniquely determine the dominant models. Thank you. Details of this study are in this publication. We look forward to questions and suggestions from you.